Welcome to my channel Biography Zone.
Early life and education. Birth and family background. Alexander Fleming was born on August 6, 1881, in Lochfield, a rural farming area near the town of Darvel in Ayrshire, Scotland. He was the third of 4 children born to Hugh Fleming and Grace Sterling Morton. His father, Hugh, was a farmer, while his mother, Grace, was significantly younger than her husband and came from a more well-educated background. Hugh Fleming had been married previously and had several children from his first marriage, making Alexander part of a large blended family. The Fleming family was deeply rooted in the Scottish countryside, relying on agriculture for their livelihood. The farm at Lochfield was not particularly large or prosperous, and life was often challenging. The Flemings lived a self-sufficient life, growing crops and tending to livestock. The landscape of Lochfield, with its vast green fields, rolling hills, and fresh air, shaped young Alexander's early experiences. Father's influence and tragic loss. Despite the family's modest financial situation, Hugh Fleming was an intelligent and well-respected member of the community. He was known for his wisdom, kindness, and love of storytelling. However, tragedy struck the family when Hugh passed away in 1888, when Alexander was just 7 years old. Hugh's death was a defining moment in young Alexander's life. The loss of a father at such an early age left a deep emotional mark on him. His mother, Grace, suddenly found herself in the difficult position of raising her children alone while also managing the farm. Fortunately, the older siblings from Hugh's first marriage stepped in to help support the family. Scottish rural childhood. Growing up in rural Ayrshire, Alexander developed an early appreciation for nature. The farm at Lochfield was surrounded by lush green fields, brooks, and diverse wildlife, providing a natural playground for a curious child. Young Alexander was adventurous and observant, often exploring the farm and surrounding countryside. Unlike city children, whose lives were shaped by industrial progress, Alexander's childhood revolved around nature, farming, and traditional Scottish rural life. He learned practical survival skills, such as fishing, hunting, and working with animals. This exposure to nature would later play a role in his scientific work, as he developed an observant mindset and a keen attention to detail, qualities essential for a researcher. Early education, Loudon Moor and Darvel School. Fleming's education began at Loudon Moor School, a small, one-room schoolhouse that served the children of the local farming community. The school was modest, with limited resources, but young Alexander excelled. He was a quick learner and displayed a natural curiosity for the world around him. Later, he moved to Darvel School, where he continued to perform well academically. The teachers at Darvel noticed his intelligence and encouraged him to continue his education. At the time, formal education was not a priority for many Scottish farming families, as most children were expected to work on the land. However, Alexander's mother, Grace, valued education highly and saw potential in her son. Despite his intelligence, Fleming was not particularly outspoken or competitive in school. He was a quiet, observant student who absorbed knowledge quickly. His teachers described him as diligent, methodical, and creative, qualities that would later serve him well in his scientific career. Winning a scholarship to Kilmarnock Academy. Recognizing his academic talent, Alexander's family encouraged him to pursue higher education. He was awarded a scholarship to Kilmarnock Academy, a prestigious school that provided a more advanced curriculum than the local schools in Ayrshire. At Kilmarnock Academy, Fleming thrived. He developed a particular interest in science and mathematics, excelling in these subjects. His teachers noted his ability to analyze complex problems and his precise attention to detail. These skills were essential for the scientific discoveries he would later make. However, financial struggles continued to be a concern for the Fleming family. Although the scholarship covered much of his education, additional expenses such as books, supplies, and transportation were still challenging. His older brothers, particularly Tom Fleming, supported him and ensured that he remained in school. Moving to London, a new chapter. At the age of 14, Alexander left Scotland and moved to London to live with his older brother, Tom Fleming. Tom was a successful doctor, and his career had a significant influence on young Alexander. For the first time, Alexander was exposed to urban life, advanced education, and medical discussions at home. In London, he continued his education at Regent Street Polytechnic, now the University of Westminster. Unlike his rural upbringing, London offered a completely different environment: crowded streets, industrial factories, and a fast-paced lifestyle. The contrast between his quiet childhood in Scotland and the bustling energy of London helped shape his adaptability and broadened his perspective. At Regent Street Polytechnic, Alexander was an exceptional student. He demonstrated a strong ability in the sciences, particularly biology and chemistry. His academic performance stood out, and many of his teachers encouraged him to consider a career in medicine or scientific research. Despite his academic success, Alexander initially did not plan to become a doctor. He was considering a career in business or engineering. However, fate had different plans for him. Influence of his brother Tom Fleming. Tom Fleming played a crucial role in shaping Alexander's future. As a successful physician, Tom exposed Alexander to the world of medicine, hospitals, and patient care. Seeing his brother's work, Alexander began to develop a growing interest in medicine and bacteriology. Tom encouraged him to apply for medical school, recognizing his talent in science. With his older brother's guidance and financial support, Alexander decided to take the entrance exams for St. Mary's Hospital Medical School in Paddington, London. Admission to St. Mary's Hospital Medical School. In 1901, at the age of 20, Alexander Fleming won a scholarship to study medicine at St. Mary's Hospital Medical School, which was affiliated with the University of London. St. Mary's was one of the most prestigious medical schools in Britain, known for its strong focus on research and innovation. At St. Mary's, Alexander excelled in his studies, particularly in bacteriology and immunology. He quickly developed a reputation as a brilliant and methodical student. His ability to observe details that others overlooked set him apart from his peers. One of the most influential figures in his life at St. Mary's was Sir Alexander Wright, a pioneering immunologist. Wright was a strong advocate for bacteriology and vaccine development, and his research focused on using the body's natural defenses to fight infections. Under Wright's mentorship, Fleming became deeply involved in bacteriological research, a field that would define his entire career. Graduation and the start of his scientific journey. In 1906, Alexander Fleming graduated with distinction from St. Mary's Medical School. His academic performance was outstanding, and he was immediately offered a position at the inoculation department of St. Mary's, working under Sir Alexander Wright. While many of his classmates pursued careers in general medicine or surgery, Fleming chose scientific research, believing that bacteriology had the potential to revolutionize medicine. This decision set him on the path to one of the greatest discoveries in medical history. Medical studies and early career. A change in career path, from shipping to medicine. Before Alexander Fleming became a world-renowned scientist, his career trajectory took an unexpected turn. Upon arriving in London as a young man, he initially found employment as a clerk in a shipping office. This was not an uncommon path for young men at the time, as the British Empire's global trade networks created a demand for administrative workers. Fleming's clerical job provided him with a stable income and practical work experience, but it was far from his passion. However, his older brother, Tom Fleming, a successful doctor, played a significant role in shaping his future. Living with Tom exposed Alexander to discussions about medicine, patient care, and the fascinating world of science. Tom recognized his younger brother's keen intellect and urged him to pursue a more ambitious career in the medical field. Encouraged by his brother's success and inspired by the possibility of making a meaningful impact, Alexander decided to take the entrance exams for medical school. This decision was pivotal, as it set him on the path to one of the most important scientific discoveries in history. Admission to St. Mary's Hospital Medical School. In 1901, at the age of 20, Alexander Fleming won a scholarship to study medicine at St. Mary's Hospital Medical School, affiliated with the University of London. This was a remarkable achievement, as St. Mary's was one of the most prestigious medical institutions in Britain, known for its rigorous academic standards and pioneering medical research. As a student, Fleming demonstrated an exceptional aptitude for the sciences. He was particularly drawn to bacteriology and immunology, two fields that were still in their early stages at the time. His keen observational skills, analytical thinking, and meticulous nature made him stand out among his peers. St. Mary's Medical School provided Fleming with a comprehensive education in anatomy, physiology, pathology, and pharmacology. The curriculum was demanding, with long hours spent in lectures, dissections, and laboratory experiments. However, he thrived in this challenging environment, showing a natural inclination for scientific inquiry. One of the most influential figures in his medical education was Sir Alexander Fleming, a distinguished immunologist and bacteriologist who was leading research on vaccines and the human immune system. Mentorship under Sir Alexander Fleming. Sir Alexander Fleming was a towering figure in early 20th century bacteriology and immunology. He was a strong proponent of vaccine therapy, believing that a human immune system could be stimulated to fight infections through vaccinations. His work laid the foundation for modern immunology, and he was particularly focused on finding ways to combat bacterial infections. Recognizing Fleming's potential, Wright took him under his wing and mentored him in the intricacies of microbiology, immunology, and laboratory techniques. Under Wright's guidance, Fleming gained hands-on experience in bacterial cultures, staining techniques, and immune system responses. Wright's research lab at St. Mary's was at the forefront of infectious disease studies, and working there gave Fleming access to cutting-edge scientific methods. This exposure significantly influenced his future research on antibacterial agents. Graduation and early research work. Fleming graduated from St. Mary's Medical School in 1906 with distinction, earning his Bachelor of Medicine, Bachelor of Surgery, MBBS, degree. His outstanding academic performance earned him a position in Wright's research team at St. Mary's Inoculation Department, a laboratory dedicated to the study of infectious diseases and immune responses. Rather than pursuing clinical medicine or surgery, Fleming chose to specialize in bacteriology, focusing on the body's defense mechanisms against infections. His decision to stay in research rather than enter general medical practice demonstrated his deep fascination with scientific discovery. During these early years, he spent countless hours in the laboratory, studying bacterial infections, immune responses, and experimental treatments. He was particularly interested in how white blood cells fought bacterial infections, and his experiments aimed to understand the body's natural defense mechanisms. One of his earliest breakthroughs came from studying phagocytosis, the process by which white blood cells engulf and destroy harmful bacteria. His meticulous research helped expand the understanding of how the human immune system naturally combats infections. Contributions to immunology and antibacterial research. Fleming's research in immunology deepened as he began conducting experiments on different bacteria and their interactions with the human immune system. Some of his most notable early contributions included 1. Studying white blood cells, he observed how leukocytes, white blood cells, attacked and consumed harmful bacteria, further supporting the theory of phagocytosis. 2. Antiseptic research. During this time, antiseptics were widely used to treat wounds, but Fleming found that many actually harmed the body's natural defenses. This would later influence his wartime research. 3. Antibacterial substances. He began exploring whether certain naturally occurring substances in the human body had antibacterial properties, a line of thinking that would eventually lead to the discovery of lysozyme and penicillin. Fleming's careful observation, patience, and innovative approach set him apart from many of his colleagues. His ability to notice small details that others overlooked would eventually lead to his greatest discovery. Military service and wartime research. With the outbreak of World War I in 1914, Fleming's research took on new urgency. He enlisted in the Royal Army Medical Corps and served as a captain, working in battlefield hospitals in France. His wartime experiences gave him a first-hand view of the horrors of infected wounds, which often proved more fatal than the injuries themselves. At the time, antiseptics such as carbolic acid and iodine were widely used to treat wounds, but Fleming observed that these treatments often did more harm than good. Antiseptics killed both harmful bacteria and the body's own protective cells, leading to severe infections in many soldiers. Fleming's wartime research challenged these widely accepted practices. He advocated for using sterile saline solutions instead of harsh antiseptics, arguing that they allow the body's natural immune system to fight infections more effectively. His observations and reports were initially met with skepticism, but they later influenced changes in medical treatment for wound infections. During this period, Fleming also continued his bacteriological experiments, collecting samples from infected soldiers and studying how bacteria developed resistance to different treatments. These investigations played a crucial role in his later discovery of antibiotics. Return to Street. Mary's and the search for antibacterial agents. After the war, Fleming returned to Street Mary's Hospital and resumed his research in bacteriology and immunology. His wartime experiences had reinforced his belief that better treatments were needed for bacterial infections, and he became even more determined to find an effective antibacterial agent. He continued experimenting with natural antibacterial substances, leading to his 1921 discovery of lysozyme, an enzyme found in bodily fluids such as saliva, tears, and mucus. This discovery provided evidence that the human body had natural defenses against bacterial infections. Although lysozyme was not effective against the most harmful bacteria, it paved the way for his later discovery of penicillin. By the late 1920s, Fleming was regarded as a leading bacteriologist, but his most important contribution to medicine was yet to come. Fleming's medical studies and early career were characterized by intellectual curiosity, meticulous research, and groundbreaking discoveries. His education at St. Mary's Medical School, mentorship under Sir Alexander Wright, and experiences during World War I shaped his scientific approach and prepared him for his historic discovery of penicillin. His early experiments in bacteriology, immunology, and natural antibacterial substances provided crucial insights that would later revolutionize medicine. His persistence in questioning established medical practices and his observational skills enabled him to see what others overlook, an approach that ultimately led to one of the most significant medical breakthroughs of the 20th century. By the time he discovered penicillin in 1928, he had already spent decades refining his expertise in bacteriology and antimicrobial research, making him uniquely prepared for the monumental discovery that would change the world. Military service and wartime research. The outbreak of World War I and Fleming's decision to serve. In 1914, when World War I erupted across Europe, Alexander Fleming was already an established researcher in bacteriology and immunology at St. Mary's Hospital Medical School in London. At 33 years old, he had spent nearly a decade working under the renowned Sir Alexander Wright, whose research focused on immunology and vaccine development. As the war intensified, it became evident that medical professionals would be essential in treating wounded soldiers. Recognizing the dire need for bacteriologists and medical officers, Fleming enlisted in the Royal Army Medical Corps and was soon assigned the rank of captain. His deep knowledge of infections and immune responses made him an invaluable asset to the British Army Medical Services, where he was placed in battlefield hospitals in France. This decision would profoundly impact his career. The war exposed him to the brutal realities of combat medicine, where he witnessed firsthand the devastating effects of untreated infections, sepsis, and gangrene issues that would drive his research in the years to come. Battlefield medicine and the problem with antiseptics. Fleming was stationed in frontline hospitals in France, where thousands of wounded soldiers were brought in from the trenches. The conditions in these hospitals were harsh and overcrowded, with limited medical supplies and a high risk of infection. Soldiers who survived gunshot wounds, shrapnel injuries, or bayonet attacks often developed severe bacterial infections due to the unsanitary conditions of trench warfare. At the time, the standard medical practice for treating infected wounds involved the use of antiseptics, particularly carbolic acid, phenol, iodine, and mercuric chloride. These antiseptics were applied directly to wounds in an attempt to kill bacteria and prevent infections from spreading. However, Fleming quickly observed that these antiseptics often caused more harm than good. Instead of effectively eliminating infections, they 1. Destroyed the body's natural healing mechanisms. Antiseptics killed not only harmful bacteria but also the body's white blood cells, which played a crucial role in fighting infections. 2. Failed to reach deeper tissues. Many antiseptics only worked on the surface of wounds, leaving bacteria deep inside tissues untouched. As a result, infections continued to spread internally, leading to gangrene and sepsis. 3. Encouraged the growth of resistant bacteria. Fleming noticed that certain anaerobic bacteria, which thrived in low oxygen environments, were actually more resistant to antiseptics than to the body's natural immune response. These first-hand observations in wartime hospitals convinced Fleming that a new approach was needed, one that could effectively kill bacteria without damaging human cells or weakening the immune system. Challenging established medical practices. At the time, the dominant belief in medicine was that antiseptics were the best way to prevent infections. Surgeons and military doctors had been using them since the 19th century, following the principles laid out by Joseph Lister, the pioneer of antiseptic surgery. However, Fleming's battlefield experiences contradicted these long-held beliefs. He noted that soldiers treated with strong antiseptics often fared worse than those who had received minimal treatment, suggesting that the body's natural immune defenses played a larger role in healing than previously thought. When he tried to present these findings, many of his medical colleagues were skeptical. The use of antiseptics was deeply ingrained in surgical and medical practices, and challenging their effectiveness was seen as controversial. Despite this resistance, Fleming continued his research, meticulously documenting cases where soldiers who received gentle treatments recovered more effectively than those treated with highly concentrated antiseptics. Experiments on wounded soldiers and bacterial infections. To further investigate his observations, Fleming conducted small-scale experiments on infected wounds. He collected samples from injured soldiers and analyzed the bacteria present in their wounds under a microscope. His studies confirmed that white blood cells were essential in fighting infections. Harsh antiseptics destroyed white blood cells before they could combat bacteria. Certain bacteria thrived in the presence of antiseptics instead of being eliminated. he began advocating for the use of sterile saline solutions instead of carbolic acid and iodine. His argument was simple: by using saline, doctors could clean wounds without damaging the immune system's ability to fight infection. While his recommendations were not widely accepted at first, they later influenced improvements in military wound treatment and laid the groundwork for modern antiseptic techniques. Post-war research, the search for a better solution. After the war ended in 1918, Fleming returned to St. Mary's Hospital with a renewed sense of purpose. His wartime experiences had convinced him that a better method of combating bacterial infections was urgently needed. He resumed his work in bacteriology, focusing on 1. Finding substances that could kill bacteria without harming human tissues. 2. Identifying natural antibacterial agents in the body. 3. Developing new treatments that could replace harmful antiseptics. His post-war research led to a major breakthrough in 1921 when he discovered lysozyme, an enzyme found in saliva, tears, and mucus that had mild antibacterial properties. While lysozyme was not powerful enough to fight the deadliest infections, it confirmed his theory that natural substances could combat bacteria without harming the body's defenses. This discovery reinforced his belief that a truly effective antibacterial agent to one that could kill dangerous bacteria while leaving human cells intact was still waiting to be found. Conclusion: laying the foundation for penicillin. Fleming's experiences during World War I were instrumental in shaping his approach to medical research. His observations in battlefield hospitals provided crucial insights into the failures of antiseptics and the need for better bacterial treatments. His willingness to challenge medical norms, his meticulous research on white blood cells and infections, and his early discoveries on natural antibacterial substances set the stage for his historic breakthrough in 1928, the discovery of penicillin. Had he not served in World War I, Fleming might never have developed the keen observational skills or the determination to find an alternative to harmful antiseptics. His wartime experiences provided him with the practical knowledge and motivation that ultimately led to the development of the world's first antibiotic, a discovery that would revolutionize medicine and save millions of lives. Discovery of lysozyme, a pioneering step toward antibiotics. Before Alexander Fleming revolutionized medicine with the discovery of penicillin, he made an earlier breakthrough that hinted at the existence of natural antibacterial agents within the human body. In 1921, while conducting routine bacteriological experiments at St. Mary's Hospital Medical School, Fleming stumbled upon an enzyme capable of breaking down bacterial cells. He named this enzyme lysozyme. Although lysozyme was not a powerful antibiotic, its discovery was a crucial milestone in microbiology. It demonstrated that the body had natural defenses against bacterial infections and reinforced Fleming's belief that bacteria could be selectively destroyed without harming human cells. This revelation laid the intellectual foundation for his later discovery of penicillin in 1928. The accidental discovery of lysozyme. Like many great scientific discoveries, the identification of lysozyme was largely accidental. Fleming was conducting routine experiments on bacteria, examining cultures under a microscope. His goal was to study how bacteria interacted with the human immune system and whether natural substances in bodily fluids had antibacterial properties. One day, while suffering from a mild cold, Fleming sneezed onto a bacterial culture plate. Instead of discarding the contaminated sample, he decided to observe what would happen. To his surprise, he noticed that the mucus had a dissolving effect on certain bacterial colonies. The bacteria in the areas where mucus had fallen appeared to be weaker or completely broken down. This observation intrigued him. What was causing this reaction? Was there a previously unknown antibacterial substance in the mucus? Fleming decided to investigate further. He carefully isolated and analyzed the affected areas of the bacterial cultures and identified an enzyme that was responsible for breaking down the bacteria. He named this enzyme lysozyme, derived from lysis, which means breaking down or disintegration, and enzyme, a biological catalyst. Expanding the research, where is lysozyme found? Realizing the significance of his discovery, Fleming began an extensive study of lysozyme, aiming to determine where it could be found and how it functioned. He quickly discovered that lysozyme was not limited to nasal mucus, it was also present in other bodily fluids. Through a series of experiments, he found that lysozyme was present in tears, saliva, sweat, breast milk, seminal fluid, egg whites. This discovery suggested that lysozyme was a naturally occurring antibacterial agent produced by the body to fight infections. Fleming hypothesized that it played a role in the body's first line of defense, helping to prevent bacterial infections before the immune system needed to respond. The presence of lysozyme in tears and saliva was particularly fascinating. Tears are constantly produced by the lacrimal glands, keeping the eyes moist and protected from environmental pathogens. Similarly, saliva contains enzymes that help break down food, but it also serves as a natural defense mechanism, preventing bacteria from growing in the mouth. How does lysozyme work? Fleming's research revealed that lysozyme functioned by breaking down the cell walls of certain bacteria, leading to their destruction. It specifically targeted peptidoglycan, a key component in bacterial cell walls. When lysozyme came into contact with susceptible bacteria, it caused the cell walls to weaken and rupture, ultimately killing the bacteria. This process is known as lysis, and it prevents bacterial infections from spreading in the body. However, Fleming quickly realized that lysozyme was not effective against all bacteria. It worked well against non-pathogenic or less harmful bacteria but was ineffective against more dangerous pathogens, such as Staphylococcus aureus and Streptococcus pneumoniae. These bacteria had thicker cell walls that were resistant to lysozyme's effects. Despite its limitations, the discovery of lysozyme was groundbreaking. It was the first time a scientist had identified a naturally occurring enzyme that could selectively destroy bacteria without harming human cells. Scientific impact of lysozyme. Although lysozyme was not the miracle cure for bacterial infections, its discovery had several important implications. 1. Confirmation of the body's natural defenses. A lysozyme provided scientific proof that the human body had built-in mechanisms to fight infections. This reinforced the idea that the immune system was not solely dependent on white blood cells but also relied on chemical agents to combat bacteria. 2. Inspiration for further research on antibacterial substances. Fleming's findings encouraged other scientists to explore naturally occurring antimicrobial agents, paving the way for the development of antibiotics. 3. Development of new medical applications. Lysozyme became an important tool in microbiology and medicine, particularly in food preservation, to prevent bacterial contamination. Pharmaceuticals, used in eye drops and nasal sprays. Medical research, as a model for studying bacterial cell walls. Although lysozyme did not revolutionize medicine the way penicillin did, it was an essential stepping stone that shaped Fleming's future research. Challenges and scientific reception. At first, the scientific community did not fully appreciate the significance of lysozyme. While Fleming published his findings in 1922, the discovery did not generate much excitement. One reason was that lysozyme was not a practical treatment for bacterial infections. Unlike later antibiotics, lysozyme only worked on weak bacteria, making it less useful for treating serious diseases like tuberculosis or pneumonia. Additionally, in the early 20th century, the concept of natural antibacterial agents was still new and not widely accepted. Many scientists remained focused on chemical antiseptics and vaccines rather than exploring the possibility of natural antibiotics. Despite the initial lack of recognition, Fleming continued to believe that his discovery